Hi folks, and welcome to the podcast on acids and bases and their effect on living things and their environment. Understanding acids and bases is very important to biology, and in order to understand acids and bases you've got to know a little bit about water as well. So what are acids and bases? Well, first of all, acids and bases form from the dissociation of water molecules. Dissociate means to come apart from. In this case, the water molecules can actually come apart from themselves in solution. Here you see a water molecule in this reaction being broken down into a hydrogen ion and what's known as a hydroxide ion. When that happens, the hydrogen that comes away has a positive charge because it lost its electron to the hydroxide ion. And the strength of an acid or a base is dependent on the concentration of the ions in solution. By definition, anything that's added to water that causes it to have more hydrogen ions in it than normal is called an acid. Conversely, a base, when added to water, will cause the water to have more hydroxide ions in it. The more hydrogen ions, the stronger the acid. The more hydroxide ions, the stronger the base. A common acid is hydrochloric acid. That's when a chlorine atom is bonded to a hydrogen atom. When that's added to water, the chlorine dissociates from the hydrogen ion and releases that hydrogen ion in water, which is what makes it acidic. Conversely, sodium hydroxide is a base. That's a sodium atom with an oxygen and hydrogen atom attached to it. That dissociates in water to release the sodium ion and the hydroxide, making the solution basic. So let's learn a little bit about the strengths of acids and bases in solution. Understanding the strengths of acids and bases is actually kind of easy, but understanding how we arrive at the actual numbers can be confusing. So take your time and follow along carefully. Now, when we talk about the concentrations of some chemicals in solution, we usually talk about the molar concentrations. It has something to do with the molecular weight of the element or the compound. Now, I'm not going to describe what molar concentration actually means. I'm going to leave that up to your chemistry teacher. All that you need to know is the concept of concentration. The normal molar concentration of hydrogen ions, and we usually denote molar concentration by using these brackets around the ion. And the normal concentration is 1 hydrogen ion in 10 million for normal water. Or, if we wanted to write that in scientific notation, we could write it as 10 to the negative 7. That's another way of writing 1 in 10 million. The concentration of hydroxide ions is also 10 to the negative 7. That should make sense because for every hydrogen ion you're going to get a hydroxide ions. If you add them together, their total concentration should be 10 to the negative 14. We don't normally write the strengths of acids and bases in the scientific notation form or in very large numbers. We have a simpler way of displaying it. We use this measurement known as pH, which refers to the concentration of hydrogen ions in solution. And it's written as the negative log of the hydrogen concentration. Water has a normal pH of negative 7. Now here's a pH scale that you might be familiar with as well. You might also know that the pH scale runs from 0 to 14. Pure water has an equal number of hydrogen ions to hydroxide ions in solution. So the pH of pure water is 7. It's also considered a neutral solution. Anything with a pH lower than 7 is considered acidic, and by definition has more hydrogen ions dissolved in solution than hydroxide ions. Conversely, anything above 7 on the pH scale is considered basic and has fewer hydrogen ions compared to the hydroxide ions. Now let's look at the numbers again. Let's look at, for example, coffee, which has a pH of about 5, which means that it's acidic. Again, that means that the concentration of hydrogen ions is 1 in 100,000 water molecules. Compared to tomato juice, which has a pH of 4, concentration of hydrogen ions is 1 in 10,000 water molecules. That's actually 10 times stronger than a pH of 5. On the acidic side of the scale, a number change is a 10-fold change in the concentration of the acid. pH of 4 is 10 times stronger than a pH of 5. Now vinegar has a pH of 3. That's the concentration of 1 hydrogen ion in 1,000 water molecules. That's 10 times more concentrated than a pH of 4. So a pH of 3 is 10 times stronger than a pH of 4 and 100 times stronger than a pH of 5. On the basic side of the scale, we'll look at seawater, which has a pH of 8. The hydrogen concentration in that case is 1 in 10 million water molecules. The hydroxide ion concentration is 1 in a million. Compare that to something that might have a pH of 9. The hydrogen concentration is now 1 in 100 million water molecules, but the hydroxide ion concentration is 1 in 100,000, 10 times more basic than a pH of 8. So hopefully now you're getting some understanding of the pH scale. It can be kind of complicated. Once you get the basic principles down, it's not so difficult to understand. But what about buffers? You may have heard of buffers in association with acids and bases. Well, by definition, a buffer is any solute that resists a change in pH. The buffers actually take hydrogen ions out of solution, or they can add them back in. An example of where buffering takes place is in your blood. Your normal blood has a pH of about 7.4, which is slightly basic. And it will keep that pH even when acids or bases are added to it. And here's why. In your blood, there is a chemical dissolved in it called carbonic acid. It's this formula right here. Now, it will dissociate in your blood into this chemical called bicarbonate and a hydrogen ion. When the reaction takes place in this direction, it actually causes your blood to become a little bit more acidic. Now, if the acidity of the blood comes too low, the reaction can reverse its direction. And the bicarbonate will accept the hydrogen ion and become carbonic acid, increasing the pH back to the basic side. This will be maintained at an equilibrium of about 7.4 on the pH scale. What are some threats to water quality on Earth with regard to acids or bases? Well, acid precipitation, you may have heard of, refers to rain, snow, or fog with a pH lower than 5.6 on the pH scale. Now, normal rain has a pH of around 5.6 to 6, which is actually acidic. So normal rain, yes, is acidic, but anything lower than 5.6 is considered acid rain. Acid precipitation is caused mainly by the mixing of different pollutants in the air with water that can fall to the earth some distance from a source. For example, pollutants produced in Europe can rain down in Asia in the form of acid precipitation. Acid precipitation can damage life in lakes and in streams. It also affects soil chemistry and can contribute to the decline of some forests. Now, human activities such as the burning of fossil fuels, that's coal, oil, and natural gas, threaten water quality because it produces a tremendous amount of carbon dioxide in the air. When carbon dioxide is in the air, it will act as a blanket or a greenhouse gas that traps heat or infrared light in the earth, causing global warming. Carbon dioxide can also mix with water in the oceans, causing the acidification of the ocean. This leads to a decrease in the ability of corals to form calcified reefs. To learn a little bit more about ocean acidification, I'm going to show you this short little video. It's about 4 minutes long.
Since the Industrial Revolution, human and natural activities have increased the amount of carbon in the atmosphere. The ocean acts like a big sponge, absorbing about a third of those emissions. When carbon dioxide dissolves in seawater, it initiates a series of chemical reactions which release hydrogen ions. An increase in hydrogen ions causes a decrease in the pH of the water, making the ocean more acidic. We call this process ocean acidification. The most significant potential impact of ocean acidification is on calcifying organisms, organisms that build shells. The building blocks of these shells are carbonate ions. As the carbon dioxide in the water increases, the amount of carbonate ions decrease, which reduces the rate of calcification and reduces the ability of these organisms to make shells. This has happened before.
According to the geological record, there have been times when the ocean pH has dropped such that calcification has stopped, or at least been greatly reduced. And those periods seem to coincide with mass extinction events, when a lot of the species have been removed from the planet. Now the question is, did ocean acidification lead to that mass extinction, or was there some underlying phenomenon that was going on that caused the mass extinction and for the oceans to become acidic? And the fossil record is just not fine enough to really tweak out which came first.
Ocean acidification also has the potential to indirectly impact other marine life. A decrease in calcification could significantly affect the food supply of copepods, pteropods, and shellfish that pollock, herring, pink salmon, and sea otters consume. This disruption in the food chain could affect many animals, including humans. Alaska is particularly susceptible to ocean acidification. Cold water can absorb more carbon dioxide than warm water. The people of Alaska are especially dependent on the ocean for their food supply and commerce. Today in Alaska, many people still live a subsistence-based lifestyle, and commercial fishing is one of the state's top industries. If ocean acidification leads to a decreased population of crabs, clams, and fish, the commercial fishing industry in Alaska may decline. This would result in a loss of revenue and jobs, as well as higher seafood prices for grocery stores and restaurants everywhere.
It's our responsibility to be here in Alaska doing this research. We need to make it a priority here that it's going to be an impact on our fisheries. So we need to be the group that makes it a priority and understands the best we can of the changes that are going to occur, and then giving that information to our policy managers at the state level.
Most scientists believe that one way to alleviate the problem of ocean acidification is to reduce carbon emissions. More research is needed to better understand how ocean acidification will impact people, economies, and communities.
This video is produced by the Alaska Center for Climate Assessment and Policy, or ACAP, at the University of Alaska Fairbanks. Funded by National Oceanic and Atmospheric Administration, ACAP provides scientific information about climate change to a range of stakeholders and helps Alaskan communities, agencies, and industry adapt to a changing climate. The video features the research and laboratory work of Dr. Jeremy Mathis, Professor of Chemical Oceanography in the School of Fisheries and Ocean Sciences at the University of Alaska Fairbanks. His research focuses on marine biogeochemistry with an application in Alaskan waters. For more information, contact ACAP at 907-474-7812 or acap@uaf.edu.
Mass extinctions. Yikes. I think we better learn a little bit more about acid acidification as scientists. That university looks really interesting. It seems like it leads to a lot of interesting jobs associated with the ocean. That's it for our introduction to acids and bases and their effect on organisms. I hope that was helpful. If you have any questions, bring them to class and we'll discuss them there.